Hello viewers, in today's class we are going to discuss another important problem from integral inequalities. And in this class we are going to discuss a very nice problem from integral inequalities in which we have to show that the absolute value of this integral, that is 0 to pi by 2 x times the square root of cosine x, is less than or equal to the square root of pi cube over 24. So to prove this inequality, we'll make use of an important result from definite integrals, that is known as Cauchy-Squarz inequality. Right? So let us first see the statement of Cauchy-Squarz inequality. See, if we have say two functions f of x and g of x defined in some interval, say a comma b, right, and fx and gx are both integrable and continuous functions, right? So now if the square of this function, that is f square, and the square of this function g of x are both integrable in the same interval, that is a comma b, right? So if f square and g square are also integrable from a to b, then the Cauchy-Squarz inequality says that the absolute value of the integral from a to b, f times g dx, is less than or equal to the square root of the product of these two integrals, right? So the first one is from a to b, f square dx, and then we have a to b g square, and here we have dx, right? So this statement is known as Cauchy-Squarz inequality. So here we have the absolute value of the integral from a to b, and here we have the integrand as the product of f and g, right? F and g, and here less than and equal to square root of the product of these two integrals. The first one is from a to b, f square dx, and then we have a to b in g square dx. So we'll apply this result to prove this integral inequality. So let us first denote this integral which is inside the mod function is by I, right? So I is 0 to pi by 2, and we have x times square root of cos x dx, right? Now see, if we compare this integral with this one, that is a to b f times g dx. So if we compare these two integrals, we can easily see that a is 0, b is pi by 2. The lower limit is 0, the upper limit is pi by 2, and the function f may be taken as x, and the function g of x may be taken as square root of cosine x. We may also interchange the functions. Either we can take g of x as x or f of x as square root of cosine x. So now we can easily see that both these functions are integrable, and their squares are also integrable in the interval 0 to pi by 2. And moreover, x is positive in the interval 0 to pi by 2, and similar is the case with cosine function, because cosine function is also positive in the first quadrant, and the limits goes from 0 to pi by 2, right? So let us find out, or let us substitute these values in this integral inequality, right? So now see, we have here the mod of I, because this integral we are taking as I, which is our this integral 0 to pi by 2 x times square root of cosine x. So mod of I is less than or equal to the square root of the first integral, that is from 0 to pi by 2, and f square. So here we have f of x as x, so f square is equal to x square. So here we have x square dx, and the second integral is again from 0 to pi by 2, and we have g square. So g square is equal to the square root of cos x, and here we have square, right? So this is cos x. So here we have cos of x and dx. So now let us take this integral as I1, this integral as I2. So I1 is 0 to pi by 2 x square dx. So the integral of x square is x cube over 3, and here the limits are 0 to pi by 2. So we have 1 over 3 outside the integral, x cube 0 to pi by 2, right? So we have 1 over 3. Substituting the limits and taking the difference, we have pi cube over 8, because this is x cube, and here we have 0, so this is pi cube over 24, right? So now let us consider this integral I2. So I2 is 0 to pi by 2, and we have cosine x dx. So the the integral of cosine x is sine x, and the limits are from 0 to pi by 2. So this is sine pi by 2 minus sine of 0. Sine pi by 2 is 1, sine 0 is 0, so this is 1, right? So now taking the values of I1 and I2 in this inequality, we have mod of I is less than or equal to square root of I1. I1 is pi cube over 24, and I2 is 1, right? So mod of I can be written as less than or equal to square root of pi cube over 24, and this is our desired inequality. Hello viewers, in today's class we are going to discuss one important integral inequality. So in this class we'll see how we can prove this important inequality, in which we have to show that the value of the integral 0 to 1 x times sine inverse x whole square dx is less than or equal to pi square over 8, right? So without actually evaluating this integral, we have to show that the value of this integral is less than or equal to pi square over 8, or in other words we can also say that the value of this integral cannot exceed over pi square over 8, right? So let us start. So let us first consider the graph of sine inverse x, right? So here we have 0, here we have pi by 2, and here we have minus pi by 2, here we have minus 1, and here we have plus 1, right? And we know that from the theory of inverse trigonometric functions, the sine inverse x, it belongs to the interval that is minus pi by 2 to pi by 2, right? So the range of sine inverse x belongs to this interval. So here if we draw the graph of sine inverse x, these are the two lines parallel to x-axis. This line is y is equal to minus pi by 2. This line is y is equal to pi by 2. So the graph of sine inverse x, it goes like this. Here we have the 2 points. So we can we can draw like this. So this point is our 1 comma pi by 2, and this point is minus 1 comma minus pi by 2, right? So the principal branch of sine inverse x lies in the closed interval minus pi by 2 to pi by 2. So now we know that when x belongs to the interval minus 1 to 1, from minus 1 to 1, then sine inverse x belongs to the interval minus pi by 2 to pi by 2, right? And here the limits of integration vary from 0 to 1. So we'll restrict ourselves to this interval, that is 0 to 1. So when x belongs to the interval 0 to 1, which is our limit, that is lower limit is 0, upper limit is 1. So when x goes from 0 to 1, then the value of sine inverse x, that is sine inverse x, it belongs to the interval 0 to pi by 2, right? So we can also write it like this: sine inverse x is less than or equal to pi by 2. So this is an important inequality to begin with, right? So we'll solve this inequality with the help of this inequality. So when x belongs to 0 to 1, then sine inverse x is less than or equal to pi by 2, right? Now what we will do, see, when sine inverse x is less than or equal to pi by 2, then the square of sine inverse x should also be equal to or less than pi square over 4. Or in other words, we can say that if we square both the sides, so we'll get sine inverse x square is less than or equal to pi square over 4. Right? Now see, here in the integrand, we have a term that is x associated with sine inverse x square. Right? So what we'll do, we'll multiply this inequality with x both sides. So we have x sine inverse x square is less than or equal to pi square over 4 times x. So now integrating both sides from 0 to 1, we'll get 0 to 1 x sine inverse x square dx is less than or equal to the integral 0 to 1, and we have pi square over 4 x dx, right? So if we denote this integral by say I, then we have I less than or equal to pi square over 4 integral from 0 to 1 x dx. So we can solve it further. So we have pi square over 4. The integral of x dx is x square over 2. Limits are from 0 to 1. So we have I less than or equal to pi square over 4, and taking x is equal to 1, we have 1 square over 2, and then taking x is equal to 0, we have 0 over 2, right? So this is I less than or equal to pi square over 4 times half. This term is 0, so we have half. So this is I less than or equal to pi square over 8, right? So this is our desired inequality. So viewers, this is how we can obtain this inequality. And here I would like to mention one important result from definite integrals. Right? Now see this inequality. So here we have x times sine inverse x square is less than or equal to pi square over 4 times x. Right? So if we denote this function by say g of x, right? And this function by f of x, right? So we'll get g of x is less than or equal to f of x. So we can also write this inequality as fx greater than or equal to g of x, right? So whenever we have two functions f of x and g of x such that f of x is greater than or equal to g of x in some intervals, say a comma b, or we can write x greater than or equal to a, less than or equal to b. So whenever we have this condition, then the integral of f of x from a to b dx should be greater than the integral of g of x from a to b, right? So we have applied this property to this inequality. And moreover, these two functions f of x and g of x should be continuous functions in the given closed interval.